Hi everyone. So this week we'll be talking about prognosis and survival. So when somebody asks, well, what's the prognosis, doctor? They basically want to know, it's code word for how long do I have to live, or what is the treatment? Diagnosis is where we talk about if a person is positive or negative for the disease. And in both of those scenarios, we have to develop instruments that can screen for the disease that we're interested in. So when we talk about validity of a test, we want to know, is this diagnostic measuring those who have the disease and those who don't? And we'll talk about key terms for distinguishing what that looks like. Sensitivity is the ability of the test to identify correctly those who have the disease. Specificity is the ability of the test to identify those who do not have the disease. And these are just terms that in epi you have to commit to memory. So sensitivity, those who have the disease. Specificity, those who do not have the disease. And when we come up with our trusty 2x2, this is what it looks like. So on your rows, which are from the top down, is the true characteristic in the population. They have the disease, they do not have the disease. And your columns are your test results. They test positive, they test negative. So you can actually calculate sensitivity and specificity utilizing the data from your 2x2. And we call it a 2x2 because literally it's 2 times 2, which is 4 little boxes. So the equation for your sensitivity and specificity is your true positive over your true positive plus your false negative. And remember your order of operations, right? You add that TP and FN before you divide your numerator by your denominator. And your specificity is your true negatives over your true negatives plus your false positives. So what is the true negative here? The true negative is the lower right box, which is your population, what is true about them. They do not have the disease, and your test accurately reports that they are negative. That is considered a true negative. And then your denominator is your true negative over your false positive, which gives you your specificity. And if you go back to specificity, what is it again? It's the ability of the test to identify correctly those who do not have the disease. So your sensitivity basically tells you who are your true positives. Who are the folks in your population who have the disease, and the diagnostic is actually telling you that they have it. And your specificity is your true negatives. Again, those who do not have the disease and the test is telling you they do not have it. Then you have false test results. We call them false positives and false negatives. If you go back up to your 2x2, a false positive is someone who does not have the disease, so that upper right hand corner, but the test is telling you that they do. And your false negative is someone who has the disease and the test is telling you that they don't. So here, I'd like you to calculate these on your own and test whether or not you got them right. And if you did not get them right, because you're either not following your order of operations or just you're not understanding, please shoot me an email. But again, if you're utilizing these equations down here, you should have no problem if I give you this on an exam calculating your sensitivity and specificity. Where students have a hard time is that they still haven't committed these terms to memory, and so they're spending a lot of time still trying to figure out what sensitivity and specificity are before they can do the calculations. So again, you have an HIV screening test example. What is the sensitivity and the specificity? For some reason you can see these. So again, work them out on your own and test yourself. Last week we talked we talked about the natural history of disease at some length, right? The Natural History Museum. What is it? It's the birth and death of a disease. Sometimes it means also the death of the host, which is your patient. Excuse me. And as I mentioned, your patients will always patients will always ask the question, well, what is the prognosis? So you're establishing again that baseline where you can compare also the different treatments that are available. And here's that timeline again for you, just in case you need a review from last week. So what is survival time? At what point do we begin to quantify survival time? So typically this time begins from the point of diagnosis, which is a little problematic when you have folks who delay care, right? They don't seek care until their symptoms have become extreme enough for them to come into the medical system. And so that's what we call the variability in survival time. The patients access care differently at different stages, and some symptoms, not all patients have the same symptoms at the same stages. So those who are seemingly asymptomatic for a period of time are difficult to detect at early stages, so that we can make sure that they're getting those treatments. So case fatality is another term that we covered last week. So this is just a review for you. The number of people who die divided by the number of people who have that disease. So if you remember attack rate, it was very similar, except that attack rate is what? Right? Attack rate is a morbidity measure, and case fatality is a mortality measure. We're talking about people who died who had that disease. And unlike your mortality rate, the denominator is limited to only cases. And what is a case? A case is someone who's positive with the disease. And your numerator is only those who die. So then we also talked a little bit about incidence density. Following all individuals is not always possible in a population. Observations on different individuals may occur at different times. So your denominator is your person time. And again, the reason that I'm reviewing this is because this sometimes is a difficult concept for folks to grasp. So if you miss class or you just want to review, here it is again. Calculate the person time. So is the answer A, B, C, D, or E? What is the total person time in person years? Look at your patients. They're labeled A to E on the left. The duration of years in the study or under observation is also 5. And then you count how many years that they were observed for each. Patient A was 5 years, patient B was 4, C was 5, D was 1, E was 3, and you get a total of 18. So your incidence is going to be 3 divided by 18 times 1,000. Why are we multiplying by 1,000? Because it's standard in epidemiology to do population rates. So we want to know the incidence density per 1,000 people, or in this case, you're looking at person years, so per 1,000 person years. That way you can compare rates from one group to another. So 166.67 per 1,000 person years. All right, so what is the person year dilemma? Do the 2 individuals at the top have the greater risk for developing disease than the other 4? Think about that for a second. So, well, the other 5 actually, right? 1, 2, 3, 4, 5. That's a typo. The 2 people at the top, their person years are 5 times 2, which is 10, and the other 5 are 5 times 2, which is 10. So the lesson here is that you can't assume that each person at risk faces the same level of risk, because the person time may seem the same, but they've actually been observed for different amounts of time each, depending on how many people. So here you see that they're illustrating it for you. The 2 people that are included in this graph, what is the period of greatest risk? Well, the period of greatest risk is actually the first year and a half, shortly after diagnosis till about 20 months after. So 2 people observed for 5 years. The period of greatest risk was the first 20 months. So understanding that, then who do you think was at the greatest risk? Thinking again about the 2 people at the top and the 5 at the bottom. Right. The 5 at the bottom were at the greatest risk for that start. And here it is again. 2 examples of 10 person years in which the period of greatest risk is from shortly after diagnosis until about 20 months after diagnosis. So you can follow those 2 people at the top forever,